All right, so let's understand what is a bipartite graph. Let me tell you, this is one of the most asked concept from graph, because it just like plugs into like multiple problems so well. Most of the time the problem will be asking you like group nodes like into separate groups, and then they might be asking you to assign like multiple colors or two different colors. Well, here in bipartite we need to focus on these two, bi and partite. So bi means two, partite means two groups or parts. So this means bipartite means, can you group all these nodes into two groups such that no two adjacent nodes are in the same group? That's all. And can you do that? If you can do that, that means the graph is bipartite, otherwise not. So this example that I've taken here, we have six nodes. 0, 1, 2, 3, 4, 5. So if you see here, and we can even write the graph for it. So this graph will be, so at each node, so 0 is connected to, we can say is connected to 1 is connected, or we can say it like this, and 1 is connected to 0, and then 2 is connected to 4. Well, before that it's connected to 1, and we are not connecting the same node to itself. Okay, so that's not an issue. And then what is 3 connected to? 4. What is 4 connected to? 3 and 5. So I think we have covered all the nodes. So 0, this is 1, this is 2, this is 3, this is 4, and I think we forgot about 5, because 5 is connected to just 4. So I will add 5 as well here. So 5 is connected to just 4. All right, so now we are complete, and this is 5th node. Now these are basically the neighbors or connected members of each of these nodes, right? Okay, all right, so this particular graph that we are given here, is it bipartite? So bipartite means grouping it into two sets. So an easier way would be, can you assign two different colors to the nodes given that no two adjacent nodes are same colors? So I can say that here there will be basically set 1, and then set 2. Can we group these nodes into two separate groups, two separate sets, such that no two adjacent nodes are in the same set? And we will do the coloring as well at the same time. So let's say I choose two colors, red and blue. Red and blue, these are the two, or maybe let's not choose this one, let's choose this one. So red and blue, I'm calling violet blue color. So these are the two different colors that we have chosen. So what we'll do, we'll start with one of the colors randomly. Let's start with red color and assign our 0 red color. So we have assigned 0 red color, so it's in set 1. So 0 is in set 1. How about next connected member of 0? So we are running DFS on it, by the way. We are running DFS. So we'll be running DFS on the neighbor of, we're running it on 0, and then we are exploring its neighbors. So since we assigned red already to 0, its neighbor, any neighbor that's connected to, they will all have opposite color. All right. So here, our next node right here, 1 is going to go into different set, and we'll assign the color violet to it. All right, and we'll also put it into different set. Now how about the members that 1 is connected to? What are the neighbors of 1? Well, 0 was a neighbor, but it's already been visited. Its color is already been assigned, so we're not going to visit that again. but next color need to be flipped. It has to become red. So this one will be assigned basically red, and it needs to be put into the group set 1. So 2. Then what are the neighbors of 2? 2's neighbors is 4. So then we'll flip the color this time. 4 will be added to set 2. Then what about neighbors of 4? 4 neighbor is 5 and 3, because these are two neighbors simultaneously need to be assigned the color, or just one by one, but they both need to be assigned the same color, and that has to be in opposite of the color that we just assigned to 4. Well, the good thing is these two nodes, they are not connected, so we can actually assign them the same color. So we can assign them red, color, and we can put both of these nodes into basically our set 1. Well, congratulations, this graph is bipartite. This graph is bipartite because we were able to group all these nodes into 2 different sets, or assign 2 different colors, such that no 2 neighboring colors, so these 2 do not have same colors, these 2 do not have same colors, these 2 do not have same colors, and these 2 and these 2 do not have same colors. So no 2 connected or adjacent nodes have same colors, or they are in 2 different sets. Now let's understand when this graph would not be a bipartite graph. Well, okay, so there might be certain scenarios. Let me tell you that whenever the graph does not have a cycle, it's always going to be bipartite, because you will always end up in a situation where like you can flip the colors as you are like moving in a non-cyclic graph. But if you introduce a cycle, it's not always the case that it's going to be not bipartite. Let me show you how. So if I introduce a cycle right here, let's say if I connect these two, then what do you see? You see that 2 neighbors of this graph have the same color. Like these two, if these 2 become neighbors, then we have two adjacent nodes that are the same color. That means that is not going to be bipartite, because we can't put these 2 into the different set, because they are the same colors, right? But what if instead of that I was introducing a cycle like here? Now you can actually, because these 2 nodes are of different colors. So what is the difference between introducing this cycle, and this cycle? Don't you see that this cycle has 3 members? So that means this has odd number of members, odd number of nodes. But this one, this right here has even number of members. So even number of members. So that means whenever there are even number of nodes in the cycle, if there is a cycle, then you can always call that, or assign, put all the nodes of that graph into 2 different sets, or assign 2 different colors. So that is a bipartite graph. But because whenever there is a cycle, and in the cycle there are odd number of nodes, then you will always end up in a situation where like you are kind of assigning like 2 different 2 same colors, the same set. So that will not be possible, because 2 neighboring nodes cannot have the same color, because that will violate the definition of the bipartite graph. Now you can see right here in the second case as well, like if I introduce a cycle here, and now we have basically 1, 2, 3, 4, and 5 members in the cycle, then also it's not possible, because we were in a situation where we were joining together 2 nodes that are the same color. All right, so now we understand the concept very well. So it's just all about running the DFS and assigning colors, and at the same time through this you can also find the cycle in the graph, because if you try to assign I mean you cannot find this cycle, but I would say like odd number of nodes in a cycle, so that could be a potential problem, right? So let's write down the code. It will be super simple. It will be just running a DFS. So what we'll do is we'll have a colors. So let me just, I shouldn't have, okay, these two colors, we can number them, it's better to work with numbers. So we can call this red 0, 0, and then we can call this violet color 1, and then we can make colors array that is going to be of same size, initially containing just -1 value. That means we have not assigned any color to any node. So we have 6 nodes, so basically 6 -1s. And then we will be basically calling a for loop. That for loop will be visiting each node. So for node in our graph, or we can say range graph. So in range length graph. So that will, because the graph could be disconnected as well, so it's not possible you just run DFS on 0 and you're able to visit all the nodes. So in this case, if in my colors, that means I have not visited it. So if this node, basically it's the index, is equals to -1, then only I would want to visit it. So I'll just call DFS on it with node and next color. So next color would be, what will be the next color? Let's start with 0, because this is the first we will be calling in this disconnected graph, or this connected graph but like just one graph. And if this is, if DFS here is false, then we can return false. This is not a bipartite graph, or we return true in the end. But let's now write this DFS right here. It will be quite short, so we'll just say DFS. It will be taking node and then next color, so I'll call it next color. So here to the node I can assign the color. So in the colors, this node, and by the way I'm calling it on a non-visited vertex, so that's why I can safely assign the color here. Otherwise I will basically try to explore all the neighbors of, so I'm gonna call it neighbors, or maybe V is a better term. So V, and I should have called this U. So this is U, this is V in graph U, at U. So this will give me all the neighbors of this. So if this V is not -1, that means if the colors at V is equals to next color, that means it's already visited and it's the same color that I need to assign. It's the same color that U is already assigned, and I'm exploring the neighbor of U, and they cannot have same color, so I can return safely false. So return false. Otherwise, else would be you need to assign the color, but like only if it's not already -1. So if colors colors of this neighbor, so v is equals to -1, then we can call DFS on it. So if DFS on v and next color would be 1 minus, we can do 1 minus next color. And let me tell you why am I doing this. Next color, let me move this code like a little bit here. Okay, so you can see. Yeah, so if 1 minus next color, and the reason is that if last color was 0, so 1 minus 0 would be 1. If last color was 1, so 1 minus 1 would be 0. So we are just flipping the color, all right, without even like thinking much about it. So, and then we can return false. Otherwise, in the end, you can return true. Return true. All right, so that would be it. And now we can move on to the coding part of this.